calibration and measurement error limit the potential of noisy intermediate-scale quantum computation. Some techniques has been proposed to mitigate this span. We compare two of them here: transition matrix and quasi-probability decomposition. The most commonly used one is transition matrix correction, which measures the overlap square matrix between our initial and final classical states, and use this information to classically correct subsequently measured data. Each element of this transition matrix is a probability we measured after preparing a noisy classical state, 0 or 1, and measured in Z basis, with an empty circuit in between. Each column of this matrix corresponding to an input state sums to be 1. Each row is a measured state. We denote this transition matrix as T matrix. If there is no span error, the transition matrix is identity matrix. E is qubit POVM. It is noisy. Rho is a noisy classical state. According to the definition of transition matrix, we have, and we can get back the ideal probability distribution while inverting this equation. This method has been widely used in experiment. A newer way recently brought up by IBM is quasi-probability decomposition. The idea is canceling error by resampling randomized circuits according to a quasi-probability distribution. This method is not limited to span error. It can be extended to any errors. The O here could be initial states, quantum gates, or measurements, but here we only deal with span error, no gate error involved. Similar to transition matrix, the methods also mitigate error based on the error information it recorded. But we use gram matrix for quasi-probability decomposition. This follows gate-set tomography. We input a set of initial states, not just classical states, and measured on a set of bases, not just classical bases. We use Pauli bases here. So each element of this gram matrix is the expectation value of the noisy density states we prepared and measured in a noisy basis we implemented. So each element of this gram matrix is the expectation value of the noisy density states we prepared and measured in a noisy basis we implemented. This gram matrix record span. They are expectation value, not probability. Span errors include error occur in state preparation and that in measurement, namely the beginning and the end, two parts. We could write it as, with B being the measurement matrix recording readout error, and A recording the state preparation error. As measurement error is usually bigger than state preparation error, in many cases, we assume perfect state preparation. This is also an essential assumption in transition matrix. And with this assumption, A is in its ideal form, so we know A, and we can calculate B with A and the gram matrix G we measured. Before we go ahead, let's take a closer look at some issues here. Quantum computers are subject to errors. We need a way to keep track of how close this actual physical quantum computer to the ideal theoretical ones. The most widely used matrix is fidelity. It is defined as, you may have noticed that When we record error information in transition matrix or quasi-probability decomposition, we are also recording the closeness of noisy observable to the ideal ones. And in transition matrix, we use probability. In quasi-probability decomposition, we work on expectation value. That is, we measure the probability of the expectation and then the disparity from the ideal ones based on the measured quantity. Probability and expectation value can be easily converted into each other. In the following study, we use expectation value, and we cannot compare the numerical values of these three quantities directly. That makes no sense. For example, we show the difference between fidelity and the disparity of expectation value in Pauli bases for 6 states of 1 qubit here. After we measure the expectation value in all Pauli bases, we could reconstruct the density matrix and calculate the fidelity. As for the disparity of expectation value, we define as this. For now, we note that even though we present this disparity as measured quantity subtracted by the ideal ones, subtraction is not what we use in error correction. This research doesn't involve much of this issue because we didn't use a difference between error here. We actually use the gram matrix. We use the subtraction to show the difference, just for now. You could also compare these results with infidelity. We hope to emphasize more about gram matrix. The fact that numerical number can be bigger than fidelity or infidelity and it can be negative doesn't mean this metric is wrong. Gram matrix is not fidelity. It is a different thing, so it could have different properties. I keep talking this because fidelity is so widely used and involved in some other methods, like randomized benchmarking. People actually just tend to compare the numerical number directly, even unconsciously. Although probability and expectation value can be easily converted into each other, we shouldn't compare the numerical number either. Actually, numbers of expectations represent the same error could look twice as large as they are in probability. So after explaining so much why we need matrix other than fidelity, fidelity is simple, clear, and popular. Why we still introduce other stuff? Think about this. If we calculate the fidelity between ground state and the superposition of ground state and excited states, that is one pole state, we get this. However, if we calculate the fidelity between ground state and any other pole states, we get exactly the same number. If the pole state here means an arrow, even though we have the arrow in different direction, we get exactly the same thing, just one number. This makes fidelity not good for error mitigation. It could be very good at quantifying quantum device, but not suitable when we need detailed error information. That's where other matrix comes in. We introduce one more thing before we go back. Pauli transform matrix representation. This is usually used in tomography. The best property of this representation may be that it contains only real elements and provides a simple way to see whether the quantum operation is trace preserving or whether the process is union. For Clifford operation, there is exactly one non-zero element in each row and column with unit magnitude. And for a composite map, it is simply the matrix product of the individual Pauli transform matrix. But we just target at span error here. we haven't made that much use of those properties. When we involve more quantum process, they will prove to be handy. However, Pauli transfer matrix is still quite useful within this study. Let me show you. A state can be represented as a real column vector. Sigma a Pauli matrix. We know that the density matrix of a quantum state can be written as Pauli transfer matrix stretch a density matrix into a clean column vector, while elements are blocks vector. Measurement operator can be represented as a real row vector. As we mainly measured in Pauli basis, Pauli transfer matrix is also convenient here. Okay, let's go back to a quasi-probability decomposition. As we only deal with span, though this all could also be quantum gates, we only look at measurement and initial states for this study. As we mentioned, measurement error is usually bigger than state preparation error. Let's think about measurement decomposition first. Say we want an ideal Z measurement. We can decompose this ideal Z into noisy measurement we could implement in a noisy device like this. Here, sigma k are rows of B. Each row of B is a noisy measurement basis, and qk are elements of the vector qb. As we know the ideal form of Z, if we also have B, we could calculate QB as. Here, QB is quasi-probability. Their real can be greater than 1 and can be negative. It is kind of another extended probability. As for B, if we assume perfect state preparation, we know the form of A and we could calculate B with gram matrix G together with A. What if we cannot assume perfect state preparation? Then we need to decompose initial state too. We could do that in the same manner as measurement. Looks great! Apart from that, we need A now. Okay, let's look at A and B. It's like the chicken or egg problem. Neither of them can be measured directly. The quantity we could get directly from a quantum device is a gram matrix. We write that in the notation of A and B because we know state preparation and measurement are actually two parts. They are actually like this. Both of them are recorded in this gram matrix. In many studies, there is a perfect state preparation assumption, and we can solve the problem easily. But if without this assumption, if we want to get A and B simultaneously, this is an undercompleted problem. It is complicated. So why don't we hand it here for a while and keep the assumption for initial state first? We can check if the assumption is right by truly implement these methods and do error mitigation. If the result looks nice, this assumption is acceptable and everything is easy, everyone is happy. Let's do it. First, look at this matrix closely. Each column of A represents a noisy initial state, but we assume it's error-free. As for gram matrix, its column is initial state and its row is measurement. Both are noisy. And note that the form of these matrices could change. The point is we need a sufficient basis, a set that's large enough so that we can write any ideal state of measurement we need as a linear combination of elements in that set. Quasi-probability decomposition can work on any measurement basis, but the transition matrix only work on Z basis. So we only investigate Z basis here. We could get an ideal Z basis like this. By the way, measurement in Pauli I basis is trivial. We could actually ignore that. If we do so, we may also take off either ground state or excited state in A. It's not a must, just to make the calculation easier. We can still get back to an ideal Z in this manner. Both are with perfect state preparation assumption. Given this assumption, quasi-probability decomposition and transition matrix methods could be related, like this. They look similar in this way, but we hope to emphasize that they are different. At least, perfect state preparation assumption is a must for transition matrix, but not for the other one. This is important. You will see why by the end of this study. So let's check the results. It looks quite good. For classical states, the expectation should be 1 or -1. Both methods can correct to perfect. For pole states, quasi-probability decomposition still works perfect, but not for transition matrix. This is very reasonable. Quasi-probability decomposition takes in more error information than transition matrix. Actually, it did see those two pole states. However, if we check another two pole states that are new for quasi-probability decomposition, it looks bad. Actually, not just bad, it looks horrible. What about the case with 3 no states, ignoring I basis? Horrible too. So perfect state preparation assumption is not valid. Actually, T-matrix methods shows similar things. If you still remember some part of the formal table, again, perfect state preparation assumption is not valid. This assumption is a must for transition matrix, but not for quasi-probability decomposition. So for the problem revealed in data, we cannot really do much with transition matrix. But we can still think about quasi-probability decomposition. The first thing comes to mind may be decomposing initial state. Right, let's not rush. As we mentioned, it involves an undercompleted problem. It is hard. Let's write down quasi-probability decomposition step by step first. Our target is an ideal expectation. We need ideal initial state and ideal measurement. We could decompose them into noisy ones, and we'd clean up. With this form, B and A are still together, and we know the gram matrix G. So imagine that if no operation betrays span, we will not really have to separate A and B. Here, QB and QA are just a bridge. Namely, we do not need true QB and QA if we just have span error. Of course, this is not really rigorous and invalid when there are other operations between initial states and measurement. But if no other operation, we could assume either B or A is error-free, so we know it. Given either B or A, we could calculate the other one with measured G. Then we have QB and QA. There is a gauge here, but that does not affect the corrected results. With invalid but simple, easy methods, we could already reach a perfect correction. By the way, we should assume A is perfect, calculate B if we do in this manner. However, in most real practice, there will be operation between span. Then we have to separate A and B, unless the error introduced in the middle of span commute with state preparation error and measurement errors. Unfortunately, this is not true for the majority. And you may ask, since we just have span here, and we could mitigate span without separating A and B. Why we failed in earlier case? That is because we did not make use of QA. We just used QB. Actually, mitigating span as a whole will always yield perfect correction. This can be seen from the math we derive. Okay, let's attack the tough problem. For an undercompleted problem, we could have multiple solutions, and we don't know which one is closer to the true physical case. So we could choose bounds and constraints based on the knowledge we know. For example, both A and B are Pauli transform matrices, so the elements should be between -1 and 1. We could add more bounds, but we have to be extremely careful with this, because adding bounds or constraints is also another way to manually add information. We should question ourselves, is the artificial information right for a real quantum device? Is that the truth? Ultimately, we are just a human. We are not quantum devices. We don't know them well. We need to be objective. Another thing we could do for this undercompleted problem is adding measured information from the quantum device, namely measuring more states for gram matrix. We don't need to worry about the validity of those information, but we do need to pay more quantum resource. So let's just explore the 3 no-states cases first. Luckily, even though we don't know the true answers and won't be able to get them, we could check if the solutions are reasonable after we get A and B. We could check the fidelity first. That one with only A should always have higher fidelity than that with whole span. This is simple, but another check is more important. We could only mitigate readout errors. If B is acceptable, correcting readout errors with B should make the corrected data better. It won't yield worse result than raw data. Okay, let's look at the data. The first failed method. And mitigate the span as a whole, as we mentioned. It always gives you perfect results. So does this one. But we do need to check if we get a reasonable A and B. Sadly, not. Especially in the last case. You might want to ask why we must check, as even with wrong A and B, we did get the perfect correction. However, though they look perfect, they are not meaningful, and they only look perfect when we mitigate both A and B together. It won't work if we only mitigate B. In many real practical applications, when we use these methods, we may only mitigate B, then we will have problem. Now, we may have to pay the additional quantum resource to get more error information. Let's think about why we got such bias correction with the 3 or 4 no states we recorded. We actually just saw part of the block sphere. However, when we record out the 6 states, the 6 states spread all over the whole block sphere. We need the knowledge of the whole block sphere to correct that. We want to see the whole picture. We need a comprehensive view. So we need to record the error information from all 6 states. This additional information helps us to get a closer look to true A and B, even though it is still an undercompleted problem and we still can't get the truth. With additional information, we test our methods, and we admit that they are imperfect cases, even with this more comprehensive error information. but we didn't see cases that are seriously wrong, like what we got in earlier case. So it is acceptable. For the cases separate A and B and correct both, the method should yield perfect correction, but it didn't. This is due to the constraints we added. How many constraints and what kind of constraints affect if it could reach perfect correction. We still put this imperfect data here to keep consistent with those just corrected B. We tried to balance everything when choosing constraints. There could be better constraints, better solutions here. As we discussed, we can find multiple solutions for this undercompleted problem. A rigorous, clever, and systematic way to find the best solution is essential. We do need further study for that. Actually, even with all those constraints, if we correct A and B together, we could get perfect correction. But we just prefer to keep those imperfect numbers, as they are more meaningful. The discrepancy shows the effects of constraints in minimization. Those constraints make the minimization harder, and the initial guess, the starting point for the minimization process, also matter. We didn't explore that, as we didn't have much clue for how to choose initial guess. Here, all the minimization started with A and B being error-free. If we correct both A and B, some defects in minimization does not affect much. But only correcting readout error is different. We have to say, in some cases, only mitigating B gave worse result than raw data. Strictly speaking, it failed to pass a validity test. Our point is they are not seriously wrong. We agree that there is room for improvement, but we don't think this is a fundamental defect for quasi-probability decomposition. It is actually interesting that when such thing happens to quasi-probability decomposition, transition matrix also performs badly, but overall, quasi-probability decomposition can show a clear advantage over transition matrix. Based on our current study, we can see that quasi-probability decomposition exceeds the performance of transition matrix, but it also requires more resources. It may offer a way to roughly separate the state preparation and measurement error, but this needs further study. We need more investigation on mitigating state preparation error. And neither transition matrix methods nor these methods is scalable, so multi-qubit case need more study. And talking about multi-qubit, we want to say a few more words. We had a study based on transition matrix last year. We tried to deal with the crosstalk between qubit with transition matrix. However, we didn't really get a very satisfying result. We haven't seen really solid evidence for how good it is based on our current small devices yet. We have to think about if the fundamental defects of transition matrix prevent dedicated study. We have no idea if this guess is reasonable. It's just my personal guess. But quasi-probability decomposition of the gram matrix does offer an opportunity. It is more precise and rigorous than transition matrix. Get-set tomography is much better at this aspect. However, it is too heavy and too complicated, at least for error mitigation. Get-set tomography is not really that practical for 2-qubit case. While for gram matrix, 3 or 4 qubit is still acceptable. Besides, the information from get-set tomography may be too detailed. With that much information, It's actually a little hard to decide how to take advantage of them. So quasi-probability decomposition, or the Gram matrix, actually kind of stand at a sweet point. It's more detailed and precise than transition matrix, but simpler and more practical than get-set tomography. We could use this to mitigate error or study the error. This was further research.